Modern mathematics relies heavily on abstract symbolic equations. We manipulate variables like x and y to find a solution. But in the classical Indian mathematical tradition known as Gaṇita, the approach was highly structural. Computations were executed through rigid, systematic algorithms. Between the 7th and 12th centuries, mathematicians like Brahmagupta, Mahāvīrācārya, and Bhāskara II needed flawless arithmetic. They were computing precise planetary periods for astronomy, dividing complex mercantile profits, and surveying land. They couldn't afford errors. To manage fractions efficiently at scale, these scholars didn't rely on guesswork or a single catch-all rule. They developed a strict four-step computational pipeline: Bhāga-Jāti, Savarṇīkaraṇa, Sama-chheda-vidhi, and Niruddha. To understand how this works, we are going to rebuild this ancient software stack from scratch. Tracing the logic of this pipeline shows us exactly how early scholars engineered computational frameworks centuries before the invention of symbolic algebra. The first step in the sequence is Bhāga-Jāti. In Sanskrit, Bhaga means a fraction or part, and Jāti means class or category. Ancient pedagogical methods demanded recognition before calculation. If a student encountered a math problem, their very first task was to identify the structural class of the fractions involved. This taxonomy tree breaks fractional expressions down into 6 specific categories. The most common ones include a simple fraction, an associated fraction, which adds a fractional part to a whole number, and a fraction of a fraction. Each class maps to real-world applications. An associated fraction, like a number combined with half of itself, was the standard format for calculating profit or growth. A separated fraction, a number minus a third of itself, was the structural model for calculating discounts and tax deductions. Classification acts as a logic gate. By identifying the exact category of the fraction first, the mathematician immediately knows which computational pathway to use, eliminating the risk of applying the wrong mathematical rule. Once the fraction is classified, the problem moves to step 2, Savarṇīkaraṇa. The word breaks down into sa, meaning the same, varna, meaning class, and karana, meaning making. This step enforces a strict mathematical law. Only quantities of the exact same kind can be directly combined. Look at these geometric objects representing a half and a third. A half divides a whole into 2 parts. A third divides it into 3. If you try to stack or add these pieces directly, they fail to align. Their base units are physically different sizes. The visual solution is subdividing both objects into 6 equal segments. Now, the half becomes 3/6, and the third becomes 2/6. The units are uniform, and they seamlessly stack together to yield 5/6. Multiplying the top and bottom of a fraction by the same number is mathematically identical to multiplying it by 1. The internal value remains exactly the same, but the outward representation changes. Savarṇīkaraṇa is therefore a conceptual goal. It is the state of uniformity, a common denominator that must be achieved before any further arithmetic can take place. Knowing that denominators must match is a theory. Actually making them match requires a mechanical procedure. That procedure is step 3, Sama-chheda-vidhi. Sama means equal, chheda means to cut or divide, representing the denominator, and vidhi means algorithm. This animation of 2/3 plus 1/4 shows the execution. To equalize the base, you multiply the numerator and denominator of the first fraction by the denominator of the second fraction. Then you repeat the action in reverse. The 3 multiplies the top and bottom of the 1/4. Both fractions are now converted into 8/12 and 3/12. They share a unified class. If Savarṇīkaraṇa provides the logical reason why denominators must match, Sama-chheda-vidhi is the brute force cross-multiplication algorithm used to make it happen. But brute force creates significant scaling issues. If an astronomer calculating lunar cycles needs to add 1/6, 1/8, and 1/12, multiplying all the denominators together creates a massive computational bottleneck. In the 9th century, Mahāvīrācārya documented an optimization for this problem in his text, the Gaṇita Sara Sangraha. He called it Niruddha, which means to restrain. On the left side of this display, we see the brute force result. 6 times 8 times 12 yields a denominator of 576. In a time before calculators, performing manual division on numbers this large consumed time and drastically increased the probability of human error. Over on the right, we apply the Niruddha algorithm. Instead of multiplying everything, we map the numbers down to their prime components, extracting the common factors at their highest powers. This isolates the absolute smallest number divisible by every original denominator. The math collapses into a base of 24. The addition runs cleanly, generating 9 over 24, which simplifies to 3/8. The answer is identical to the bloated calculation on the left, but requires a fraction of the computational effort. Niruddha, known today as the least common multiple, didn't change the underlying mathematical truth. It removed friction. It allowed complex mathematical systems to scale up without collapsing under the weight of their own arithmetic. Viewed together, these 4 steps form a complete computational pipeline. A raw word problem goes in. You classify its structure, establish uniform units, select the equalizing algorithm, and optimize the numbers. The solved equation passes cleanly through the end. This specific toolkit formed the bedrock of Indian mathematical sciences. It made precise land surveys possible, streamlined complex tax calculations, and allowed astronomers to predict eclipses. Figures like Mahāvīrācārya and Bhāskara engineered scalable code for the human mind. They defined strict operational rules anyone could follow to guarantee accurate outputs. Ultimately, the classical Gaṇita tradition prioritized the design of elegant, logical systems over the mere derivation of a numerical answer.